I want to take a look at another visualization of orbits. So it is slightly simpler and closer to where we are in this class, and as you can guess what this represents, right? What does it represent?
Is it the sun and the earth?
What?
Is it the sun and the earth?
Yellow is confusing, and last time it was the sun. Yellow this time is the earth.
Oh, okay.
And so the blue is the moon. And there is no need for the sun because here it is entirely fixed, so there is no need for it to be on a specific, there is no modeling of the sun itself. So it's purely, it is a purely parametric curve in the sense that there are two curves. And first of all, this is just a circle, okay, so pure circular motion, and you can turn it into, actually it is actually, there's an option to make it an ellipse, which is the true shape of the orbit, and then they combine with another circular or elliptic motion of the moon around the Earth, okay? So as you can see, unlike what I did last time, which we had only three rows, here that is a spreadsheet, and every point is this. So for example, if I take this, U is the Earth, X is the Earth, okay? And so these 2 points, the two numbers, give you a point on the XY plane. Okay, so in that sense, you can recognize what we're talking about. We're talking about functions. So just two functions with the same independent variable. Independent variable is here. A table of values increasing gradually, and there is one output is the x, the other output is y. So independent variable is t, and x and y are two dependent variables. So the tricky part that, unlike what you have seen previously, the t does not appear here. Well, there are not enough dimensions. So we have x dimension, y dimension. So every point appears as a dot, and there's no place for t. So if we want to plot t as well, you can imagine what's going to happen. What does it look like?
Three-dimensional.
Yeah.
Three-dimensional.
Yeah. Okay. So, it will be three-dimensional. So x, y, and t. And can you imagine what the graph of the Earth would look like?
Kind of like a tube almost.
Yeah. So we'll be moving along a tube like this.
Yeah.
So it's like a spiral. Spiral, screw, or what is the helix is the word, the technical term. Okay, so we're going to do this later. Any kind of motion can be modeled in that manner. As you can see, this one is the sort of the solar system has been solved here by whoever, and then they gave us the parametric curves. Unlike what you saw yesterday, the curves are given and we just plot them. Okay. So and the tricky part, we're not going to pursue this until later because as you can see, this will plot the Earth here, circle. Then U is the moon. It's also circle, but with respect to the Earth. Okay, so to plot the moon, however, we have to do x plus U. So that is a vector operation. So it's much easier to understand this if we have vectors at hand and we use it to model things. Whether it is an object thrown or like the cycloid, another example of a parametric curve, and so we'll do that later. So that's why I want to start with we started yesterday with something simpler and more tangible in a way, and that is a curve that comes from some very simple place. And we can, and then once we understand what we've got, we'll plot it. We'll come back to Excel and we will create a from scratch. So this is I don't want you to think that you would expect to produce this instantly. You do it step by step, and it just happens to be more than one parametric curve plotted here, so it looks big. But otherwise, plotting a parametric curve is fairly simple affair. So. Okay, so that's what I started with here. Okay, over here. which is the definition, still somewhat informal definition of a parametric curve. Two functions of the same variable with the same independent variable, but the two dependent variables might be different. And incidentally, one point I want to make is in this case, x and y are unrelated to each other, and therefore they can be plotted on any xy plane. They can be plotted separately, together, it doesn't matter. If we're talking about actual motion, the challenge here is well, you can see what's wrong with this picture. Look carefully at the axes. 50, 20, 40.
The scale's off.
The scale's off, yeah. So if you're plotting any kind of motion, then you have to deal with that because they have the same units. And you cannot stretch one and shrink the other because actually if you say switch from kilometers to miles, you have to do both in both directions. So the circle remains a circle. If you stretch it that way, your circle becomes an ellipse. So that is just a stand in the way. It's extra complexity added to the problem. And here, as you can see, it doesn't matter. So even though both measured in dollars, but you could measure one in millions and the other one in thousands. I mean, price of wheat, say, it could be per wheat or per bushel, okay, and maybe sugar per ton. So you can really think of these two variables as unrelated, and these are two indeed at this point unrelated functions, unrelated to each other. Okay, so I want to take this example as far as I can and then end up plotting it. So let's make our functions before we actually get to do any kind of calculus. Let's just understand what parametric curve is. While there is no the term, I want you to be careful about the looking at the word curve literally, because this is a curve, but this one isn't. There is no curve. So if you see a motion and you have a trail, you have a path, it is a curve, and you want to understand it, you use parametric curve or parametrized curve, as some books prefer. I'm not sure what that book says, but in mathematically speaking, just two functions of the same independent variable. Okay, then they turn into a curve. Okay, so I want to take these two functions then and say something specific about it. So price, well, let's imagine a scenario of something happening to the price of wheat, price of sugar, and then we'll see if there's anything that we can do to understand the economics of with two commodities total. Okay, so the price of wheat, let's say, let's just start by describing verbally. So let's say, so x, how about is just plainly decreasing. Okay, so it just happens over time. The price of wheat is decreasing. Okay, so. And well, that all we can say. But if we want to make it specific, and just for the sake of illustration, then we want to have a formula. So I want to have a formula x of t. So if you have seen parametric curves, then it's most of the time it's x and y or x1 z later on, and these are, so the variables are, the x is typically now is the dependent variable, one of the dependent variables. So t is the independent variable. So give me an decreasing function of t.
Negative t?
Yes. The only problem is that we don't want negative prices. How about, can you think of something like this?
How about t squared minus t across 1 and 0 and 1?
T squared minus t. You know, t squared, it will increase eventually. It's just you have t squared. How about 1 over t? How about 1 over t plus 1? T greater than 0. Okay, so let's suppose time starts at 0. I don't want to divide by 0. So we know what the graph roughly looks like from calculus 1. So at this point, as long as you have only one function, everything that we know from calculus 1 will be applicable. Okay, so we don't care about what's happening to the right of 0, but this is my t and this is my x. Okay, so all right, so this is pretty much it. If you want to review things from calculus 1 and the meaning of functions, so to continue with the point I just made, it is ultimately a table of values. So you have t's, you have x's, and if you want to plot this, if you already know the answer, you draw it with one curve, one by one stroke of a pen. But if you don't, and that's a more typical situation, what you do, you plot values. Initially, you do it by hand, and then you proceed and you do it with either Excel or something else. So we'll stick to Excel. So, but say I have 0, 1, 2, and 3. So what do I have? 1, 1/2, 1/3, 1/4. I could, to get this curve that I have, I will plot these points, 1, 1/2, 1/3, 1/4. And well, plotting these 4 points gives me the idea of what's going on. And at this point, maybe if necessary, I proceed to calculus. By calculus, I mean calculus 1. Okay, so I will study derivatives. I will look at the rates of change, maximum and points, although that you remember from calculus 1. Okay, so one function, except this time we have 2 functions, and we'll have to study 2 functions. Okay. So let's take the second one, and y is the price of sugar. Let's suppose it goes up and then, how it goes up and then down. Up and down. Doesn't matter. So can you give me such a function? I asked for a function that is never negative, but let's suppose it's some. So we could take like an upside down parabola. So upside down parabola looking like this. Can you, like maybe like this, something like this. Remember how parabolas moved, how you move graphs around by changing either x or y, x.
Can you just make the t negative from the previous one, from 1?
No, I'm not sure what, you want to take the previous?
Yeah, and just turn the parabola upside down, or your curve from number 1.
No, it doesn't have an extreme point. This is what I want an extreme point. So I'm thinking parabola. So parabola, as you can see, this parabola shifted from 0 to say this is 1 and this is 2. Okay, so it is parabola shifted first horizontally, then vertically, then turned upside down. Or rather, how about we turn it upside down first and then we shift it. So remember how it is done?
So would you have like negative and then like t plus 1 in parentheses squared? And
So
then
so we start with the t squared. That is our regular parabola turned upside down, which gives me what? What's the formula? Negative t squared. Okay, now to shift it vertically, what do I do? Shift vertically by 2.
2 minus t squared?
No,
Plus
vertically.
2.
Vertically. Plus 2, that's it. And finally, to shift it 1, you use the right.
T minus 1.
If you replace t with t minus 1. Okay, so this is what it produces. T minus 1 squared plus 2. Okay, so it's roughly, we'll have this formula. The other x, so the x-intercept is, what is it? 3? 3, no, yeah, no, wait a minute. No, it's not 3. Well, let's not worry about that. Okay, so once again, you can have a table of values, and you can once again plot them separately like this. You have like this t and y, and you plug in 0, 1, 2, 3. I plug in 0, I have 1. This is 2, I plug in 2 and I have 1, is it? I plug in 2, 1, and I plug in 3, I have, hold on a second, that's not right. If I plug in 1, I have 2, if I plug in 2, I have -1 plus 2, it is 1, and I plug in 3, 2 squared, 4, is it, what am I doing wrong here?
That'd be -2 for like 3.
For 3, -2, oh yeah, that's right, negative. Okay, that was. So roughly, this is roughly 2, right? And then it goes faster down like this. So there's between 2 and 3, it has the quadratic. Okay, so that's all good. And once again, calculus 1 to be used, not much of used for calculus 2. Well, actually, before we discard calculus 2, first of all, we're going to be using integration, then whatever you've seen about parametric curves. But thirdly, there is one issue also we already have seen from calculus 2 that will be useful, and that is, well, what do these look like? Look at these numbers. Rather than looking at t's, look at these. Sequences, right? So we're actually thinking about sequences as far as modeling is concerned. Plotting we're not going to pretend that we're plotting actually the whole curve, because it always the same thing. We're plotting it from this. Every plot is just a bunch of points, and they're plotted in this manner. Okay, so ultimately we're plotting sequences, and there is another issue here. Unlike remember how yesterday we computed from location, current location. We know current location, current velocity, and we know our next location. Remember that? That's how we did the rotation of the Earth around the Sun, for example. Okay, unlike this one. This one starts with the curve, but what we did yesterday was, you remember the word for those sequences when the next is computed based on the previous one? Recursive, right? So recursive sequences are the best when you do plotting of curves that there's some kind of dynamics there, such as forces or velocities, flows, whatever. And then once again, you don't care about the past. All you need is your current place, and you find the next one. The most important example of recursive sequences in calculus 2 was what? You know the answer. I'm asking in a confusing way. Series are recursive, so you add a term every time. Okay, so this is all not untypical. Okay, so sequences will be big then again, even though we don't care about the limits not much. What we do care about right now is how to take this information, 2 pieces of information of data. And later on, our ability to study them separately using calculus 1. Okay, how do we combine them together and at least visualize, to begin with visualize before we proceed to calculus of parametric curves? How do we visualize this? And it's not really that complicated, because if we already have the idea, the arrangements have been made that so the dependent variable, the independent variable is clearly marked as by the same letter t, so there's no confusion. Okay, then once again greater than 0, and then x and y are the output variables. The dependent variables are marked with different letters, and they're conveniently marked in such a way that you recognize that this must be something about xy plane, x and y. So plot something on the xy plane, right? So that's the idea of parametric curves. That's where the parametric curve will appear. So make one curve from those 2. So these are the 2 graphs, and that supposedly it will reveal something about the economics, how these 2 might interact, or they don't interact. Essentially, they are not interacting, as a matter of fact. So the price. We don't know, or we don't care about how the price of wheat affects the price of sugar, but we just take the data. In fact, the data most likely will come. It's not going to come in this form, right? We're just making it up. It will come in this form. The data will come in numbers, so it might be changing every day or every second. It doesn't matter. It will still be a table. So that's what they do. They do the spreadsheets. That's what they do on Wall Street. for the most part, they use Excel. So the data comes in form of data rather than formulas, and we just pick this to make our illustrations easier, so we don't have to make it up. And then if you want insight in the discover possible interactions of the price of sugar and the price of wheat, and hopefully maybe draw some conclusions. Okay, so that's what we were after, and we already know what to do. The analogy we will be coming back, in spite of what I said about how you need vectors here. We will be coming back to this. So you can think about what we have here is a motion through space. This is motion through space, only what that space is. You see what the space is? No, time remains time. Okay, so in both of these two examples, this one and the last one, hold on a second, it is still time. It will be time, and we'll stick to this. It's hard to think of any better idea for like a metaphor for the independent variable of a parametric curve. But the space, this one moves through our space as we see outside, just two-dimensional. And here we are moving through the xy plane, except now x and y have nothing to do with physical space, but rather it is this made up space of prices. So, and you can imagine if you have 100, or typically, I don't know, could be easily 10,000 commodities being traded every day. So there you have 10,000 dimensional space. Okay. So, okay, but let's suppose we have only two. If you have 10,000 dimensional space, it's impossible to visualize anyway. So we have two-dimensional, so we're still in a good place, and that's where you start, so you can build up intuition. So at some point you can say, well, I understand parametric curves, I don't need pictures anymore. Okay, so we will be plotting. So what we will be plotting, can you see from these two tables? This is how we plotted the graph. The first graph, the second plot we plotted. Now let me circle these. So for example, this point we plotted over here, and on the other hand, I plotted this one over there. Okay? What is the relation between these 2 points? T, only T. So x and y is unrelated. They happen to be the same. X and y equal to 1, but really they are related to each other. So what do we plot then?
Just
One. Well, we only plot x and y. So the point that we actually take from this is 1, and here 1, and together they form a point 1, 1, and that point is the only one that is plotted. And then we proceed in the exact same fashion, taking this one, oops, and the next one. So the next one will be 1/2 and 2, and so on. Okay, so let's do that by hand, and then we'll do it with Excel, so that we can have a nice picture. Because by hand, you can see it's not going to look good, or it's not going to tell us anything. I'm choosing the first quadrant, so that just assuming that we only care about positive prices, otherwise it's just meaningless. Hypothetically, so the first point I'm plotting is 1, 1, right? So 1, 1. Well, I probably need marks here. 1, 2, 3, 4. So these are x's, these are y's, and I plot the first point 1, 1. The first point is 1, 1. The second point is, once again, we're referring to these two little tables, and 1/2 and 2. Okay, 1/2 on the x-axis. Well, I guess okay. It is on the x-axis. I pick one. This will be 1/2, and then I pick 2 over here. So these are 2 marks that together produce the second point. Okay, and then the next point. What's the next point?
1/3 of 1.
1/3 of 1. So it's got to be here somewhere. Oops. 1/3 and 1 here somewhere. Okay, and finally, well, the negative number we'll ignore, but at some point between, at some point it hits 0. maybe here somewhere. Hold on a second. Where does it crosses the y becomes 0 at some point, which means that we're crossing the x-axis. If you look at the picture, so this one certainly doesn't have enough information for us to say a lot about what's going on. But if we just have points, 3, 4 points might be enough. And as you can see, it will continue the pattern of if we are moving in that direction. And that it will be going down. So you can try to guess what's going on and maybe add some curves like this. Okay, so very strange picture, and you have to extract it, but it does contain information about just about all the information about the two original curves. So you can see through what point we pick. We can pick on the point over here. We know that is the price. There was a price, a combination of prices. So you say this point is maybe 0.7 price of the wheat and 1.7 price of the sugar over here. Okay, this is a different price with the same price of the sugar, but the price of the wheat is different because, as you can see, the price of the sugar went up and then down. Okay, so that picture doesn't tell a lot, and without doing more, you are lost because there's just to do it point by point is too hard. Let's just do Excel and from scratch, and we'll see that it's really not that complicated. So let's make it start. Okay, from scratch. From scratch, we have two functions. Let's just start let's repeat what we did over here, and we just make it nicer. So we have a formula. The graph we remember from Calculus 1, but otherwise we can certainly do a better job. And then we'll go on to and then we'll plot the parametric curve too. Okay. Okay. So 1 over t plus 1. 1 over t plus 1. Okay, so one thing, so we won't have something like this. So what we want to have is always the time parameter, interval parameter over there, h. Okay, so this is how far we will be progressing. Okay, so that's the first step I make. I choose h. Okay. Okay, so I choose h. And it doesn't matter. How about 0.1? Okay, so this will be the parameter. The time will progress by this parameter. So I'll put t here, and I'll put x here. So once again, I'm doing one of these two functions at a time. So I'm doing the wheat first. Okay, so t and x. T will start with 0 as we want. Okay, so I'm not sure how well you were familiar with with Excel. So the next one should be 0.1. I want to the 0, I want to add 0.1. So you know how it's done?
It's cell A2.
Yeah.
If you want it to be 0.1.
I prefer, as you can see, I prefer the more mathematical approach when you both have numbers vertical and horizontal.
Okay.
Ultimately, it pays off. So the easier way is actually to do what you suggested, is to click on the previous one, and then you add, so the previous one plus what? Plus the value of h. Okay, so this time, yeah, I cannot click on it, otherwise it will be just copying things incorrectly. So it will be R2, row 2, column 1. Okay, see how it happened? All right, so previous plus the entry, whichever that is, the fixed entry in the second row, first column. Okay, so you can see the two cells here next to each other. The first reference is relative, a so-called -1 stands for the previous row, and the second one, R2C2, is the absolute reference. So it is always will be, as I'm going to be copying next. Oops. Yeah, okay. So as I'm copying next, I will be adding, control down, okay? I am getting, every time, add +1. As you can see here, if I take, say, 0.1 over here, the formula is the same. So I take the previous element, the relative reference, -1, and I'm adding h, which is absolute reference in the second row first column. Okay, so now I'm writing the formula for x. What was the formula for x? So I'm just writing equal to, remember the formula?
1 over t plus 1.
1 over, so once again, this will be very similar to your homework, by the way. So if you write 1 slash, what's the next symbol?
T.
No, parentheses. Okay, so it makes a difference. So t plus 1. Okay, there is no t. We make a reference to the previous element, like this. Okay, going horizontally. Okay, so this is t, indeed. C negative 1 means the previous column. Okay, and then I write plus 1. Parentheses. Okay, and I go down, control down, I fill it, and I have a bunch of values to make it more pleasant to look at. I'll pick a number here. So these are the values. I don't have a lot, but at this point, this is a function, a sampled function, our function, the formula that we have, which gives you the price of wheat as a function of time, and we can just plot it. So insert one of those. I prefer the Scatterplot. So as you can see, that's one. This is truly, Excel plots truly what you see. What you see is what you get. The every point is a dot. Okay, if you want to fool somebody and pretend that it's actual curve, you do this. There's another one. Okay, so it interpolates and put a curve through these points, which looks very natural, and it hides the points. Okay, whichever you prefer, I don't know. Most of the time I prefer this one, so we're not fooling ourselves. We know that it is based on the dots is our curve. Okay, it is ultimately a sequence, even though not an infinite sequence. Okay, so once again, this is our wheat in one of the two functions. Now we move to the second function, which without making it too difficult, I'll just copy and paste, and then I'll just write a new formula. Okay, so this will be y now this time. So the independent variable, no need to change it. This is my independent variable. Okay, so all I need to do is change the formula. So I do not remember the formula. The formula is negative t minus 1 squared plus 2. Okay? So I'll just start typing. Let me erase it. Okay, equal, negative, parentheses, right? Then what do I do?
Reference
T.
I click on this one. Is it minus 1?
Yes.
Minus 1, parentheses, squared. Once again, that all from either a calculators or that online homework, that this is symbols, plus 2. Okay, so that changes only 1 point, and okay, this one refers to the wrong data. Okay, and this one is the same, but that's still cool. Okay, so this is our sugar, as it depends on time. Okay, so once again, two functions that have nothing to do with each other. And what do we do to plot to only what we want? So if what we did over here, plotting only x and y's and ignoring t, it's exactly the same story. It's exactly the same story. You just insert the Scatterplot. Okay, so insert. So I go with the Scatterplot, say this one, and here I'm supposed to choose data. Okay, so let's say this is x, and this is x. So I'm choosing for the x values of these many points, whatever 17 points. I choose the x values. Okay, then yeah, that's it. Okay,
Professor.
yeah, yeah.
When we were doing it, it says that it says that the function of y is 3, and when we did it, it was 1.
Functions of y.
Whenever you did you put the t0 into the y function, it gave you 3.
So did
Should there be like
What
There's-
another
hold on a second.
parentheses around the exponent, so the 2 isn't included in that?
Yeah, so it does the negative after.
Yeah, you're right. Yeah, sorry about that. Okay, so in other words, no, hold on a second. We went up and down. So if I, so -2? No, wait a minute. No. Why is it? It doesn't look right at all.
The numbers are right. I think the parentheses need to be moved around.
Yeah. So what did I do wrong here? Negative. It still doesn't look right. I mean, this is what happened. I lost it.
There's a negative in front of
Let
the...
me just fix this. This picture doesn't look right. It is supposed to be a quadratic polynomial. It definitely should point down. Why is it pointing up?
There should be a negative in front of...
Yeah, there is a negative over there.
There
You
is?
can't
Yeah,
see
that's
it.
why I was wondering if you put
It is there.
If
There's
you
no-
put a
there's
parenthesis
a
around
little
something.
negative.
Yeah, then I think around the exponent, there needs to be an extra
It
parenthesis.
should still point down.
Right.
Why is it not pointing down?
Is the order of operations in Excel different?
I think what it's doing is
Yeah.
applying the negative before it squares it.
Right, and then it's giving you.
No, I mean, it's not that stupid. Minus parenthesis square. Oh, you negative and then squared?
Right, and
Mhm.
then it's
Yeah,
like
I think that's what it's
three
doing.
instead
Yeah,
of.
it must be what it is that stupid. I've been doing it for a while. I never encountered this bad treatment of numbers of order operations. That's what it did. It first took minus and then it squared it, and that's why it's pointing up. Well, okay, let's try to fix it, and then we'll get to the parametric curve. So we'll put more parentheses. When in doubt, just put a bunch of parentheses. Like this. No, like this. Okay.
Yeah.
Okay. Okay.
Oh, that's better.
Oh.
Wanna get that?
Okay. Okay. So, all right. Excellent. Okay, so it's upside down, 1, which is 1/6. We could extend it a bit further if we like. In fact, let me show. I could just make this one slightly smaller to have a more complete picture, or slightly larger. So this one extends, and this one extends too. Okay, so we reached it at about 2.4. We have an excess. Okay, now how do we make a parametric curve? Let me try just to mark rather than doing it the long way. Is these will be x's and these will be y's, and I'm not sure if it works. Let me try at least. No, probably won't understand it. So insert. If they were side by side, would have been. I don't get it. Why is it?
That's just attaching them.
It's for some reason trying to change the chart that I already made. I want a new one, but it starts to change it. Okay, so. Okay, so let's start over. So I'm inserting a new scatterplot. Okay, this one. Okay, so it's totally new scatterplot. These remain, and I just need to choose data. And for scatterplot, it will be x and y separately. So I'm choosing. So add 1. So this will be 2 points x, y at a time. Okay, so I'm choosing values for x. And these are the ones. Okay. And I'm now choosing values for y. And these are the ones. And now it should work. Okay. Okay. It does not look what I plotted at all. Why doesn't it look it? Well, no, it looks very much like what we had. It just stretched. Okay, so confusing part is we're moving in the opposite direction. This is the time progresses in this direction. Okay, so follows, this is one, remember? So that's why when you do parametric curves, it's a good idea to provide markings or labels to every point, because so that you catch the missing variable, the time. So for example, I would put here, I could actually do it physically. And let me just copy. I think I can do it. I thought I could. Let me try again. I should be able to copy and paste. And maybe not. Yeah, well, they're not all that easy. So anyway, so if you draw it, if you have it on a piece of paper, or otherwise want to actually provide a complete picture of a parametric curve, then it's very descriptive, but reveal it. But you have to mark the at least the direction. Incidentally, there is a way to provide arrows, so at least you know in which direction time progresses. So let me hold this. There is an option of that data series. Oh, this is 10. No, I have no idea where things are. Okay. Yeah, so I still have Windows older version, and it still has different. Maybe it's design. No. So anyway, I'll do that next time. So you can change. You can have an arrow following from the point data point to the next data point. At least you will know that the time goes from right to left. And you can imagine it looks like a function, but you can imagine that it doesn't have to be a function or graph or a function. It could make this turn right easily. That's the difference between parametric curves and graphs of functions, is that you could have curves that are not graphs. Okay, so they could violate what? The vertical line test. So the vertical line test, which tests whether or not given a curve is a graph of function, we certainly know that they could have circles. If you continue this on, you'll have a circle, and that is an example of a violation of vertical line test. But we don't care, because everything can happen. And okay, so let's try to first appreciate what has happened. So these two graphs of they are unmarked x's, but we do remember that the horizontal axis is the independent variable t, vertical is x. Here, the independent x, dependent y. Then x t's are thrown out, and we are having here the dependence of x and y. And x and y are not in the same way treated as in calculus 1, because now y does not depend on x. Neither x depends on y. In fact, we know where it comes from. Both x and y depends on t, so that's why there does not have to be the graph. So let's try to let's confirm that this graph indeed reveals the information that we started with. Remember, the price of x, the price of wheat, is decreasing, and in fact approaching zero, right? Let's see, it has an asymptote. Okay, so and for y it goes up and down, and then becomes negative. The price, that is. Okay. Okay, so can you see it here in this graph? Yeah.
I have a question.
Yeah.
This might be a dumb question, but since we're taking out time, we're just plotting x and y. What does this graph tell us?
Well, that is a question, right? That's what I want to try to discuss. It's supposed to tell us the dynamics of wheat versus sugar.
Right.
So maybe there is a hidden relation between them. You have two functions, and if they are complicated enough, there might be a relation between them, and the relation can be actually be very revealing. So it's really not that hard to imagine that. Well, let's make that discovery quickly. We have a couple of minutes left, so let me. So suppose so ignore the formulas. Okay, ignore the formulas. And suppose I will give you ignore the formulas that I'm entering. Okay, so that's what we've got. So the price of wheat is this. The price of sugar is this. Okay, so it seems like they have similar behavior, and then you plot this, and then you do the parametric curve. So can you predict what the parametric curve might look like?
Y equals X.
Close. You see that is a relation. Turns out that the price of wheat is exactly, or sugar is exactly the price of wheat. Okay, so who knew? So that's a revelation. Just looking at these two graphs, these numbers are really what comes to you, and you don't know anything. It's just numbers. They don't tell you anything. Neither graphs nor data tells you anything. But you plot the parametric curve, and suddenly something comes out, and you have a big discovery. Okay, so. Any questions? All right, come on.
You might need both of those stuff. Yeah.